This will be a more high-level talk, mainly because the topic of this talk is quite different from the topics that have been covered in the talks previously today. But it has to do with complexity in some way, because it has to do with complexity in the context of artificial intelligence, and especially in the field of large neural network-based language models. So okay, let's see if this is working. Nope. Yeah. Okay. So I assume that all of you already have heard about ChatGPT. Okay. This is a question that I asked to ChatGPT, so to generate a brief abstract for a talk about large language models for DCP23. And this is the title and the abstract generated by ChatGPT. And it's quite good, also from a very linguistic point of view, but also from what concerns the content of this title and the abstract generated by the model. And well, in this talk, I would like to first of all give you an overview of what is it a model like ChatGPT, how are built, and how this large language model works. And then I will focus more specifically on the topic. So one of the more vivid research area in the context of natural language processing and artificial intelligence in the context of language model, that is the interpretability of neural network-based models. Okay, so I will start saying that a neural language model is a complex model. It is based on a neural network, and it is a neural network that is trained to approximate a specific function that is the so-called language modeling function. What is it, the language modeling function? It can be seen as a simple way of defining the probability of a sentence, okay? And the probability of a sentence can be seen as the probability of a word in a sentence, in a context, according to the previous context, okay? So predicting a word according to the previous context, okay? And in 2003, Benjo and colleagues proposed for the first one to define a model based on neural network to solve this language modeling function. This was the first instance of the first case of the so-called neural probabilistic language model. And so this is the idea. We have a neural network that starts with a sequence that, for instance, could be I saw a cat on A, and then we ask the model to predict the next word according to the previous context, that is I saw a cat on A. So the next token word could be on a table, on a mat, and so on, okay? From that day, 2003, until now, a lot of improvements have been made in this context. Nowadays, we are dealing specifically with transformer models. That is the most commonly used architecture for developing these models. The transformer that was introduced in 2017, it's a neural network architecture that exploits this so-called attention mechanism to create contextual representation of words and learn relations among them. So the attention, it is a mechanism that can help the model to focus on single word in an input sequence, also looking at all the other words in an input sequence. So creating contextual representation of words, of meanings of words and sentences. So from 2017 until now, a lot of improvement have been done in this context. A lot of models have been developed, and also the size of these models increased a lot in the last 5 years. We go from like BERT model that was introduced at the very beginning of 2019, and it has 340 million parameters, and now we are dealing with very large models like GPT-3 or GPT-4 that has more than 170 billions of parameters. And for instance, we don't know how many parameters has the GPT-4 model that was introduced 2 months ago. For instance, this is another image that shows the graph of all the models that have been developed from 2019 until now, that can be seen as large language models, so models that have more than 10 billion parameters. And we can see here that we have ChatGPT and GPT-3, GPT-4, even if we don't know how many parameters this model has, okay? So this is the core idea of a large language model. A large language model is simply a neural network with different kinds of architecture, even if the main architecture nowadays is the transformer one. And it is a model trained to approximate the so-called language modeling function, okay? One of the most addressed line of research in the context of artificial intelligence in general, but also natural language processing, is the idea of interpreting and trying to understand the inner mechanism of these models, because these models are often seen as black box models. We have an input, we have an output, but we don't know how these models behave in its internal mechanism, in its internal representations. And so a lot of techniques and methodologies have been implemented in the last few years. Also in the context of my research field, that is natural language processing. This is a quotation from a work of like 4 years ago that says that it was very simple to understand the behavior of traditional machine learning based system in which we know the input and which we know the mechanism of these models. Now it is more difficult to understand what happens in a neural network that takes as input and then generates an output. So there are a lot of questions in this context, in the context of artificial intelligence and also natural language processing. So what happens in a neural network model when it is trained on this language modeling function? What kind of knowledge, linguistic knowledge, semantic knowledge this model knows in their internal representations? There is a relationship between the ability of the model to solve a specific task and then to understand implicitly linguistic knowledge. And so the analysis and the interpretability of these models have become one of the most addressed line of research in the last few years in the context of natural language processing. A lot of methods have been implemented to obtain explanations and also to understand how this model captures syntactic and semantic phenomena. A lot of techniques have been developed. And well, for the rest of the talk, I would like to introduce some of these methods, okay? And I'm sorry that I have to introduce to you some aspects of linguistics, but I will be very high level in the introduction of these concepts. For instance, this is one of the first work that have been introduced since the introduction of the transformer-based neural language model. This is a work based on the BERT model. It's a transformer model, and it is a work done in order to understand the behavior of the model on a very specific linguistic task that is the subject-verb agreement. I will show you what is it, the subject-verb agreement task. The core idea of this work is we can somehow take an input sentence, an input sequence, we can mask a word in that sentence, and then ask the model to predict that word and see if the model is able to predict the correct word that is underlying this masked word. So the core idea is that we have, for instance, a sentence that is the game that the guard hates his bed. Here we have, in terms of linguistic, an agreement between the subject of the sentence, that is the game, and the verb, that is. So the core idea in this work was, let's mask the verb is. Let's ask the model to predict the word that is beneath mask, and see, for instance, if the probability of is higher with respect to the probability of bar, okay? So the correct agreement. And in this work, Goldberg showed that these models are quite good at solving these tasks, also in very complicated configurations. Also, in some configuration, they are better than humans, okay? And this is a score that was obtained with a model that was introduced in 2019. So probably ChatGPT, GPT-4 is more able to solve these tasks. And this is one of the possible approach that has been developed in the last few years to study these models. Another approach that I used to perform some experiments in the last few years is so-called the probing tasks approach. The core idea is that we have our neural network. We can feed the model with an input sequence. In our case, our input sequence is a sentence. We fed the sentence into the model, but we keep all the weights of the model frozen, okay? We extract the representation from the architecture of the neural network. We fed these representation, these are simply vectors, okay? into another model, generally a very simple linear model, a linear regressor, a linear subprofector machine. And we ask this model to predict a simple linguistic property of the sentence that we fed into the neural network. The core idea is that if this simple linear model, this so-called probing model, is able to solve this task with quite good accuracy, we can somehow assume that this knowledge is implicitly encoded in the representation of the model, the original model that is the transformer model, okay? For instance, following this approach, 2 years ago, we proposed a work in which we decided to find a way to profile a neural language model. Again, this is more related to linguistics than artificial intelligence and machine learning, but this so-called linguistic profiling approach assumes that we can extract automatically from a text a lot of features that can describe the syntactic and morphosyntactic structure of a document, for instance, and we can use these features with a predictive model to profile a text or profile an author, okay? And so we decided to extract these kind of features to profile a neural language model in order to understand if these models are able to implicitly encode linguistic information, even if these models are not specifically trained to understand this kind of knowledge, of information. And so we replicated this probing task approach. So the core idea is that we have a sentence, why would you want a chihuahua? We fed this sentence into our model. It is a neural network. It has several layers. In that case, we used a model with 12 layers. We fed this sentence into the model. We extract the representations from the model, and specifically, we extract the representation only from one word in a sequence, that CLS, that very briefly, it can be seen as a sort of a summarization of all the semantic and syntactic information of that sentence. We fed this representation into a linear model, and then we asked the linear model to predict simple properties of the linguistic structure of that sentence, okay? We use a tool that is a tool that we developed in our group that we can use to extract features, linguistic features from a text. So we simply take a document, fed this document into this tool, and extract a set of features that can describe the structure of a document. For instance, how many words a document have, how many verbs, how many nouns, the complex syntactic structure of a document. And these are the features that we would like to understand if the model, the transformer model, is able to encode in its internal representations. So in this work, linguistic profiling of a neural language model, we investigated the linguistic knowledge implicitly encoded by a BERT model. We try to understand if the model is able to encode these kind of linguistic properties. We investigated how this knowledge is modified after we fine-tune the model, and fine-tune means training again the model to solve a specific task. And then we investigate the implicit knowledge, how this knowledge affects the ability of the model to solve these downstream tasks. I will very briefly show you only two images. Here we can see the results of the pre-trained model, so the model that is trained on the so-called language modeling function. And then the other one is the fine-tuned model. So this is the model that was, again, trained on another task. This was a very linguistic task that was try to identify the native language of a writer that writes in another language. So for instance, the text is in English, but the writer is French or Italian. And let's identify the first language of this writer. And the curves here, and you have in the x-axis the 12 layers of the model, in the y-axis the performance of the model. And we can see here that the model is able, with quite good Spearman correlation scores, to encode different level of information, properties of the syntactic and morphosyntactic structure of a sentence, even if we didn't train the model to solve the specific knowledge, only looking inside the internal representation of the model and training a probing model with the internal representation of the model. And another interesting results that we found is we can notice that we have quite sort of a drop of performance across the 12 layers. So when we go to the first layer, to the output layer of the model, the performance of the model tend to decrease, and especially we notice this behavior when we use the fine-tuned model. And this has been shown that is a property of the behavior of these models that tend to specify to their target task at the expense of implicitly encoding some information that we are inspecting in its internal representations. And this is one of the possible way of inferring the knowledge, syntactic, but also probably semantic and other kind of knowledge that are implicitly encoded in these models. Okay. For instance, another approach is the so-called analysis of attention mechanism. I said to you previously that one of the main features of these so-called transformer models is the attention mechanism. The attention mechanism can be seen in this way. When we are processing a word in an input sequence, we can see how this word attends to all the other words in a sentence. So in that case, we can say that when we are dealing with the pollution word, the model also to compute the representation of pollution is also looking at was, at caused, and at shipwreck. Okay, so a lot of works started to investigate these attention mechanisms that are simply matrices, so the attention matrices inside the model, and see if there are some kind of knowledge that it is implicitly encoded in these matrices. And for instance, this is a work proposed in 2019, where the author showed that if we focus at different layers of a transformer model and also at different heads, because in each layer we have more than one attention matrix. In general, we have 12 attention matrices per layer. So we have 12 layers, and for each layer, 12 attention matrices. And if we look at different combination of layers and heads, we can notice that, for instance, the model pay attention to different words in an input sequence, and that has been shown that, for instance, the model, when we are in the first layers, is simply attending to the next word. When we are looking into the representation of the middle layers, the model start to create create a graph related to the, for instance, syntactic knowledge of a sentence, so the links between words into a syntactic structure, and so on. So a lot of works try to understand how these attention matrices can be used to infer the implicit knowledge encoded in these models, and then, of course, how this knowledge can be a proxy for understanding why the model takes a specific decision in a specific downstream tasks. And well, I would like to simply conclude that neural language models you already seen with ChatGPT and other models like that have reached astonishing performance in a lot of context, but the improvement of these models comes at the cost of their interpretability. They are complex models, mostly difficult to understand how they behave, how they make some kind of decisions. And so a lot of methods have been implemented to understand how they behave and how they make decisions. And this is an ever-evolving, exciting research area of research, and a lot of possible future directions. So study, for instance, how this linguistic knowledge in the model arise during the pre-training phases. So when we are training the model, how this knowledge arise, try to improve the robustness of these models. For instance, selecting input data in an appropriate way in order to have a model that is more robust to a specific structure or to a specific task, and other kind of possible implications. That's it. Thanks for the attention.
Thank you. Thank you, the speaker.